Welcome. We have been discussing radiation, and in the last class we discussed how you could describe the energy that is being carried by a ray, and I told you that this could be described, this could be quantified in terms of the specific intensity or the brightness, which is denoted by I nu. And this quantity is defined for a so for a ray we have a particular specific intensity, and we have defined the specific intensity in such a way so that it tells us the following thing: if we place an area element of size dA normal to the direction of the ray and ask the question, what is the energy coming into this area element from the solid angle interval d omega in the direction of the ray. So, the energy incident in this ray is given by the specific intensity into the area element, into the solid angle, into the time interval, into the frequency interval. So, this tells us the specific intensity tells us the energy incident that is being transported by this ray, which is also the energy that is incident on this area element dA from the solid angle d omega. So, it is from a specific direction, range of very small range of directions, in the frequency interval d nu, in the time interval dt. That is how the specific intensity is defined. So, this is called the specific intensity or brightness, and this is what we use to characterize, to quantify radiation. Provided you are dealing with length scales which are much larger compared to the wavelength, where we can think of light as rays. And then in the last class we studied certain properties of this specific intensity. I told you, actually I showed you, that it is conserved if light propagates in vacuum. So, if light propagates freely in vacuum, the specific intensity does not change along the ray, right. We saw this in the last class, and we saw various other things that you could calculate. Once you knew the specific intensity, you could calculate the flux, you could calculate the pressure, and various other things. Today we had, in the last class we had just briefly started discussing what happens when light propagates through a medium, and that is what we are going to discuss in today's class, right. So, let me start off where we had, let me just briefly repeat what we had discussed right at the end of the last class. So, we were considering emission, the emission of radiation. So, our attention is on a particular ray, and it is travelling in a medium. So, this is the medium, and our ray is not in a single direction, it is in a small range of directions in a, so in the solid angle interval d omega. So, this is what we are interested in the solid angle interval d omega, in the frequency interval d nu, in the time interval dt. That is the energy that is incident. So, we are interested here in rays travelling in the solid angle interval, directions in the solid angle interval d omega, and it is the light here is propagating through a certain medium. So, the incident energy, we have already calculated this. Let us say that this has a volume, the incident energy is, let us first calculate the incident energy. Let us use S to label the points along the ray and this is S plus delta S. This point is S, this point is S plus delta S, ds you may say, okay, S plus ds. Now, the incident energy on this surface, let us call this surface dA, we just saw how much the incident energy is. The incident energy is I nu at the point S into dA d omega d nu dt. Now, we next define something called the emission coefficient J nu. So, this medium through which the light is passing is also emitting radiation. So, when the light comes out, the energy that would come out would be the light that is incident, the energy that is incident plus whatever has been emitted by the medium in between. Now, the emission coefficient is defined in such a way so that J nu into the volume element. So, here what is the volume? The volume here is ds into dA. This is the energy that is emitted out in the solid angle interval d omega, in the frequency interval d nu, in the time interval dt. So, the emission coefficient tells us the energy that is emitted in a particular solid angle d omega, in the time interval dt, in the frequency interval d nu by a volume dV, where here dV is dA into ds. That is the volume that the light is going through. That is what gets added to this ray. Okay. So, the light that comes out is now the specific intensity, sorry, A nu at the point S plus ds, and everything else remains the same. So, with this definition of the specific intensity of the emission coefficient, it essentially tells us per unit volume the energy emitted per unit in that particular per unit frequency interval, per unit time, per unit volume, per unit solid angle. Okay. So, with this definition of the emission coefficient, the difference in the specific intensity in the length interval ds is J nu. So, from this we can straight away say that dI nu ds is equal to J nu. So, when the ray traverses a distance ds through a medium with emission coefficient is J nu, the specific intensity, this is the rate at which the specific intensity changes, okay, or this increases by an amount J nu ds. Okay. So, this is the emission. So, we model the emission process. Here we are not going into the microscopic detail of how the emission occurs, right. We are not going into the microscopic detail of how the emission occurs along the ray. We are just quantifying whatever mechanism you have through this emission coefficient, which tells us that per unit volume, that is the energy emitted in this solid angle d omega, in the frequency interval d nu, in the time interval dt, which is of our interest. Okay. So, this is, and as a consequence of that, the specific intensity changes like this. Let us now quantify the absorption. That is the other possible process. So, we are looking at absorption next. Okay, that is the next thing of our interest. And here so we have the same thing, we have a ray which is propagating, and it goes through a medium. So and the question is, what happens to the specific intensity when the ray has traversed through a length ds through some medium? It will get absorbed. In general, there will be emission and absorption both. So how do you quantify the absorption? And for this there is the something called alpha nu, which is the absorption coefficient. Okay. Here again let us go through the same exercise. So the incident energy per unit, we are interested only in a certain solid angle. So the incident energy is I nu into dA d omega d nu dt. Now the energy that gets absorbed here, this is at the point S. Okay. So at the point S, and the energy that gets absorbed is alpha nu times I nu into dA, the volume. So the absorption, the energy that is removed by a volume dV is alpha nu into the incident specific intensity into the volume. Again we have all those elements, the solid angle, the okay, and this is equal to the specific intensity at the point S plus ds So the absorption process, again doing the same thing. So the absorption process now gives rise to a decrement in the specific intensity, and the decrement we see is di is given by di nu ds is equal to minus alpha nu I nu. Okay. So let us try to just get a picture of this, of why we have written it in this way, that it is proportional to the incident specific intensity into some absorption coefficient. So consider a hypothetical situation where we have a volume, this is the volume that we were interested in, dA ds, and in this volume we have small absorbers distributed, microscopic absorbers, and each of these absorbers has a scattering cross section of sigma nu. That is the scattering cross section, it is the area which each of these microscopic absorbers, these small absorbers, that is the scattering, that is the area which it through which it absorbs. So the incident energy is, let us just ask the question, what is the total area that is actually absorbing? So these absorbers have a number density n. Okay. So let us assume that there are these small absorbers with number density n. So n of these absorbers per unit volume, and each one has a surface cross section area scattering cross section of sigma nu. That is the area which it presents for absorption. Okay. So, let us ask the question, what is the total area covered by my absorbers in this volume? To do that, we have to take the number density and multiply it by the volume. So, that is the total number of absorbers. Each absorber has an area sigma nu. So, that is the total area which is presented by these small absorbers, and the total energy that is absorbed now is going to be the I nu, the incident specific intensity, into this area, into the solid angle, into d nu dt, right. So, this is the energy loss that is going to be caused by these small absorbers located over here, which with number density n and scattering cross section sigma nu, right. So, which is why we have written it, which is one picture which kind of gives us a feeling for why we have written the scattering the absorption term as the incident specific intensity into some absorption coefficient, and here we see that the absorption coefficient can also be written in terms of the scattering cross section of these individual microscopic scatterers, and it can be written like this, where sigma nu is the scattering cross section, the area of each of these small absorbers, and n is the number density. Okay. This is also quite useful sometimes when we know the scattering cross section of the individual microscopic absorbers. So, now we are in a position to combine both of these and write down the radiative transfer equation, which tells us what happens to the radiation as it propagates through a medium. Okay. So, let us write down the radiative transfer equation now. So, this is called the transfer of energy through radiation, radiative transfer, which is very important in astrophysics, and the equation now has, we are interested. So, this is the situation that we are considering, is that we have a ray of light, we are interested in a particular ray of light, S is some distance parameter S along the ray, and the equation, radiative transfer equation, is the derivative of the specific intensity with respect to S. So, there will be an input of energy due to emission, and that is given by J nu, and there is a removal of energy which is given by minus alpha nu I nu, right. So, this is the radiative transfer equation which governs the propagation of radiation, with which we can use to study how radiation propagates through any medium. Okay. So, the rest of this class is largely going to be devoted to the discussion, to the analysis of this equation, right. So, let us start off by discussing two simple situations. The first situation is where we have only emission. So, if you have only emission, so this is going through a medium. So, we have a medium over here, right. So, as the light propagates through a medium, the absorption, we can, let us suppose that the absorption is very small, it may be neglected, and we are it is the emission that is important. So, the light is propagating through this medium, it is the emission that is important. In that situation, we can forget about this, and then we have I nu, this let us say is S equal to 0, where it enters the medium, okay. And we are interested in I nu as we go along the ray. So, this is increasing S. So, I nu at some point s is I nu at s equal to 0 plus the integral 0 to s. Now, the emission coefficient can vary inside the medium, it need not be a constant. So, I have a j nu s prime d s prime, and if it is a constant, then the problem is very simple. I have just got the emission coefficient into the length. Okay, so that is how the specific intensity increases then. Okay, so that is one of the simple situations. The other simple situation which we encounter quite often is where you have only absorption, and we encounter this very often. For example, light is propagating through a slab of glass or through some water or through the atmosphere when we look at the stars. So, in any such situation, you typically it is absorption which is important and not the emission. So, in such a situation where you have only absorption, here again the solution is rather simple. So, here we do not have the emission term. So, you can bring this I nu onto the left hand side and integrate this, and we can straight away write down the solution without going through the mathematics. The solution is I nu s, so s is some point inside the medium, is equal to I nu 0. So, when you bring the specific intensity onto this side, you will get a log of the integral of alpha nu into s ds. So, when you invert the log, you get an exponential. So, this is the incident specific intensity into exponential minus 0 to s alpha nu s prime d s prime, right. So, it decays exponentially. If the absorption coefficient is a constant, then it just decays exponentially with the increasing length minus alpha nu into s. Okay. So, this is how the specific intensity changes with the increasing distance inside this. Now, we are interested in a situation next where we have both emission and absorption. So, the question is how to solve the equation, the radiative transfer equation. In such situations, it is convenient, it is very convenient to introduce something called the optical depth. So, let me introduce the optical depth. And we use the symbol tau to denote this quantity called the optical depth. And this is a very useful and a very interesting quantity if you are doing radiative transfer. Okay. So, this optical depth, so the way we proceed is that we divide this equation with the absorption coefficient alpha nu. Okay. If I divide this equation with the absorption coefficient alpha nu, then we have over here we have d tau is equal to alpha nu ds. Okay. And this is called the tau is the optical depth. So, we can integrate this and determine tau. So, tau, the optical depth, it is a function of s obviously, and this is 0 to s alpha nu S prime d s prime. This is the optical depth. Okay. So, we are interested in the propagation of this light into this medium. S is 0 over here, S increases inside, and the optical depth is the integral of the absorption coefficient into ds as you go inside the medium, and you integrate till the position you want to calculate it at. Okay. Now, what does the optical depth tell us? Let us take a look at this. Okay. So, to get a clear picture of this, there are a medium is said to be optically thin or optically okay. If tau is less than 1, a medium is said to be optically thin. So, it is said to be optically thin. So, let us see what it implies. You see this term over here, what happens to the specific intensity as you go inside the medium? It falls off exponentially, right, and it falls off exponentially as e to the power minus the optical depth. So, if the optical depth is small, say my medium is only this much and my optical depth is small, so this is a small number. So, my specific intensity, whatever goes in, largely comes out. There is very little loss inside, right. If this number over here is quite small, is very small, then the exponential is very close to 1, and whatever goes in roughly comes out. There is a very small attenuation inside. Or we can say that the chance of a photon which enters this medium coming out without being absorbed is quite high, right. The average photon does not interact with this medium, does not get absorbed with the medium, by the medium, it just goes through and comes out. Okay, so this is what is called optically thin. This is a medium that is optically thin, and we would also call it transparent. Okay. So, the typical in such a medium, the typical photon just goes through the medium without interacting with it, without getting absorbed. Okay. So, typical photon here just goes through the medium for an optically thin medium. It is transparent. The typical photon goes through the medium without experiencing any absorption, without interacting with the medium. Such a medium is said to be optically thin, and this is measured by this quantity tau. Okay, such a medium is said to be transparent, and this is measured by this optical depth tau. Tau greater than 1 it is optically thick. So, such a medium is said to be opaque. What do we mean by this? So, this is the optical depth, and as the and that is going to contribute by this source function. Okay. So, the point over here at some tau prime is going to contribute, and it is going to again suffer an attenuation, that is not the entire tau, but the difference tau minus tau prime by this much, right. So, we have to take the source function at this point and attenuate it by e to the power minus tau minus tau prime, and then add up the contribution from all of these points, which is this term over here. Okay, so, this is the contribution from the radiation along the path, and each point the contribution gets attenuated again as it propagates through the medium. Okay, so, this is the formal solution to the radiative transfer equation. Now, as an example, let us, so we can first of all straight away see that we recovered the very simple situations that we had considered right at the start, where there is only emission and where there is only absorption. Those you can recover straight away. Let us now consider a situation where the S nu is a constant. It does not change with position, it is a homogeneous medium. The source function is a constant. So, we are going to assume that S nu, the source function, is the same throughout this entire region. Okay. If the source function is the same through this entire thing, we could then do this integral, this term will come outside, and e to the power minus tau will also come outside. So, we have an integral of e to the power tau prime d tau prime, right. We have just an integral of e to the power tau prime, because this minus and minus sign here, e to the power tau prime d tau prime, and the limits of the integral are tau to 0. So, if you do this integral e to the power tau prime, let me write down the integral. So, we have the integral, the second term now becomes e to the power, this s comes out, e to the power minus tau comes out, and we have e to the power tau prime d tau prime, right. That is the second term. The first term is unchanged anyway, the second term becomes this, and this can be written as s e to the power minus tau, and we have e to the power, the integral of this is again e to the power tau prime. So, at the two limits we have e to the power tau minus 1. Okay, so, this is S 1 minus e to the power minus tau, right. So, we have just evaluated the second term, and we can now plug it back in this. So, if I plug it back in this, what do I get? I get the fact, the solution is that I nu, the specific intensity is the so, we will have a constant term S nu, yes, the subscript nu is there throughout, so at a particular frequency. So, this is going to be S nu plus we have this term already here, and we have this term which has to be added you have to integrate this divided by c over all solid angles, right. This is the radiation force on some medium. So, when a medium absorbs radiation, it also absorbs momentum, and you have a force, net force. You can have a net force. If the radiation is coming from one direction, you will have a force in that direction being acted upon on the medium, being acted on the medium because of the incident radiation getting absorbed. Okay, and this is the force. It is the incident radiation specific intensity into the absorption coefficient divided by c, because that is the relation between the momentum and the energy, integrated over all solid angle, and n is the direction. So, you have to consider rays in all directions. Okay. So, let me end today's class over here. Tomorrow we shall continue our discussion of radiation a little further.